And that means that's our final H prime, which consists of two terms, and different to what we had last week on Tuesday when we did perturbation theory and we had perturbation Hamiltonians. This now actually, because it has a term linear in the perturbation, linear in the vector potential, and therefore also linear in the magnetic field or in the magnetic moment. Here we have now a first order of perturbation, but we also have this term. That's quadratic in the vector potential, therefore quadratic in the magnetic field or quadratic in the magnetic moments. So we get a second order Hamiltonian, which means the expression which we used on Tuesday last week, or we looked at, we have to modify it because now we actually have also a second order Hamiltonian. So all the general nth order equations, you have to fill in one extra term always, where you have a second order Hamiltonian also showing up now. Right, so we can the whole thing we can combine now in a Hamiltonian. So the Hamiltonian in a general, in this semi-classical minimum coupling with a general expression for the, for the vector potentials and the scalar potentials somewhere up there. We end up then, let's see, when we get everything, our Hamiltonian is, and that's in the Born-Oppenheimer, so it's the electronic Hamiltonian. Let's start with kinetic energy. That's what we have here. 1 over 2 me sum over I pi squared. Then we can, let's take that linear term here first. So we get E divided by me, not 2me, me, sum over I, the vector potential at the position of electron I times its canonical momentum. Then we could add all the, well, let's add the quadratic term also here. E squared divided by 2me, sum over I, the vector potential squared. And let's add now all the scalar potentials, the expression with the scalar potentials, and that means those extra ones, but we also have all the normal ones because we have a potential for the interaction of the electrons with the nuclei, which is that Coulomb potential. We looked at, we have nuclear repulsion potential, which we typically add to the Hamiltonian, although you don't necessarily have to do that. And we get our last week favorite electron repulsion potential. And instead of writing them as V, let's really write them out. That's the sum over nuclei, sum over electrons. It's the position vector of the electron minus the position vector of the nucleus. Then we have the charge of the nucleus, and that's so far actually it's just the potential. And then like here, we have to multiply that with the electronic charge, which is E minus E. So in total we get ZA E squared and a minus sign there. Then we get that with both nuclei, which is then RA minus RB, ZA, ZB, E squared. They have the same charge, so we get a positive sign. And then we have sum over all unique pairs of electrons. Ri minus Rj E squared plus, again, so those are the three potentials which we always had. And to those we get now the extra potentials from the electric field, which is again minus E sum of I phi of for the electrons and positive contribution. For the nuclei, A, we have ZA, the same potential, but now at the position of a nucleus. Right, and I mean this thing, that, and those two are together our H prime, the perturbations, the extra terms. The next thing we can do is to insert the expression for the potentials and to look at all the different kind of real perturbation operators and then assign them to which property they belong. Because so far I only have now the potentials in the Hamiltonian. Now I have to insert my expressions for the potentials and see what kind of operators we end up at the end.